Unit 4.1 Quadratic Equation in Vertex Form. In this chapter, we're going to learn the transformation of a quadratic equations. So here's our class objective: to identify and graph quadratic functions. It's pretty easy to identify what a quadratic equation is, and the challenge is to sketch the graph of a quadratic functions. So a couple terminology or concept that you have to pay attention to are: first, parabola; next, axis of symmetry, and vertex. Parabola is something like this. Axis of symmetry is a line actually cut the parabola into half. Vertex is the point. We're gonna go into more details in the next slide. Here's the vertex form of a quadratic equation. If you still remember what we have learned in Unit 2.6, the families of function, this is exactly what we learned in, not exactly the same, but very close to our absolute value function. And the general formula for absolute value function is y equal to a absolute value of x minus h plus k. Remember that? We have exactly the same thing, except right now we use a parenthesis instead of an absolute value sign, and more importantly is the square here. When we learn to identify quadratic equation, we look at the power. When the power is equal to 2, it is a quadratic equation. I want you to pay attention to a couple important things about quadratic equation. First, this type of curve, we call it a parabola. So every quadratic equation is actually a parabola. The next thing is this line. We call this line axis of symmetry. The reason we call it symmetry because they basically cut the parabola into half, and say if this is a mirror, you can actually overlap this line on this line when you fold it. And of course, this point, this is a very important point, we call it a vertex. And the coordinate actually is from the generic formula of the vertex form of a quadratic equations. Now if I draw the coordinate plane, you may see it more clearly. So the red line here is the axis of symmetry. The x coordinate here for this line is h, and the y coordinate for this vertex is k. That's why we write down the vertex h and k. H is the x value of the vertex, k is the y value of the vertex. So let me put down x and y here for you. Now say you have an example of a quadratic equation in vertex form, which is y equal to, I make it simple, so say a only equal to 1 and x minus 4 whole square plus 2. I try to line them up for you. So x minus h here whole square plus k. So we know a equal to 1, h equal to 4, and k equal to 2. So the axis of symmetry gonna be x equal to h, so x equal to 4. So we know the coordinate here is 4. And the vertex is gonna be 4 and 2 is a point. This is the vertex. So we know the vertex right here is 4 and 2. The value of here for y value of the vertex, of course, is 2 right here. Next, we're going to see the transformation of quadratic functions. So we all start with parent function. Parent function means the simplest form of any function. So in quadratic function, the parent function is y equal to x squared. This is the simplest form for quadratic functions. And all the other quadratic functions are developed from here. That's why we call it parent function. For the parent function of a quadratic function, the vertex is 0, 0. And the axis of symmetry is x equal to 0. Some people will not understand why. If you change the parent function y equal to x squared to the vertex form, which is gonna be y equal to, say, x minus 0 whole square plus 0. If you simplify this expression, you know you end up getting the same thing, x squared. But by writing this, you know the value of h, this is h, is equal to 0, h equal to 0, and k equal to 0. And that's why the axis of symmetry is where x equal to h, but this time h equals 0. And the vertex is h and k, which is 0 and 0. Remember, the vertex is h and k. That's why for parent function, the axis of symmetry is x equal to 0 and the vertex is 0, 0. And by the way, if you don't know the expression of f of x, you may want to just replace f of x, is basically means y. Before we learn the transformation of quadratic functions, let's write one more time the generic formula for a quadratic equation in vertex form. So y equal to a x minus h whole square plus k. Now let's learn the first two transformations of quadratic functions, which are translation and shift. Translation refers to the movement of up and down, and shift refers to the movement of left and right. And if we want to know how does the curve move, we have to look at these three variables and the sign here too. So we have to look at a, h, and k. And the last one we're going to look at is a sign, in front of the variable a, whether it's a plus or minus. So let's take a look of translation and shift first. Remember, h control the movement of right and left, and k controls the movement of up and down. So take a look at this. A lot of people will be confused by this one. When you say x minus h whole square, look at h and pay attention to the sign minus. So if we say x, in this case, say 1, 2. So if you say x minus 2 whole square, that means this is the parent function, will move 2 units to the right. So shift to the right by 2 units. A lot of people will think, oh, negative, so you have to move to the left. No, because the original formula is minus, so the value of h is actually positive 2. So that's why we moved the parent function to the right by 2 units in this case. How about k? K is a little bit easier now. K control the movement of up and down. So in this case, the blue is the parent function. If you say x squared plus 2, for example, that means it translates up by 2 units. And if you combine these two movements together, say you have x minus 2 whole square plus 2. The blue one is the parent function. In this case, that means it moves to the right by 2 and then translate up by 2 units. Does it matter which one we go first? It doesn't matter. You can say it goes up by 2 first and then you shift to the right by 2. Now we're going to talk about the last 3 transformations of quadratic function, which involves reflection, vertically stretch, and vertically compress. So I have to highlight this for you. Vertically stretch and vertically compression. Before I start, I have to rewrite the generic formula of quadratic equation in vertex form one more time. So right now, let's start with stretch and compress. You know H control the movement of the shifting to left or right, and K controlling the translation of up and down. A is the factor. So if A is less than 1, bigger than 0, which most of the time is a fraction, say half, then we call it vertically compressed. Okay, this is vertically compressed because we push from the top to make the curve actually wider. But when A is bigger than 1, say this time is 2x squared, we call it vertically stretched. In other words, it is getting narrower. The last transformation that we're going to learn is reflection. Reflection is referred to the sign here. Without any sign, it's a positive. When it is positive, it opens upwards like this. But when the sign is negative, we call this reflection. And if I have negative, say negative 2 x minus say 3 whole square plus k plus 5 equal to this whole thing. When we see negative 2 right here, when you see negative, actually I would say when you see the sign negative, you know right away it reflects across the x-axis, so it would open downward. And this one we refer it as open upward. And when the curve is open upward like this one, we have a minimum value, which is the vertex. But if the curve open downward, we have a maximum value, which again is the vertex. Now let's learn how to interpret a vertex form of a quadratic equation. If you're given a quadratic function or equation in this vertex form like this, what would the vertex, axis of symmetry, the maximum or the minimum value in the domain and the range? The best way to answer this question is to sketch the graph of this equation. So the first step, we just line up the question with the generic formula of the vertex form. So when we line them up, we know A equal to 3 and H equal to 4. K, be careful now. You can actually change it to like plus minus 2. Plus minus 2 is equal to minus 2. But if we write it this way, we know K is actually minus 2. So K is minus 2. From this we know the vertex HK is 4 and negative 2. So if we try to graph it now, so we know the vertex is 4, 0, x, y here. So we know the vertex 4 right here, negative 2 right here. So say 4, we know the vertex is going to be right here. Here's the vertex. The next thing we know, the line of symmetry, the axis of symmetry is x equal to 4 and x equal to 4. So we know the axis of symmetry is right here. This is the axis of symmetry, which is x equal to 4. And because the a value is 3, we know it's bigger than 1. 3 is bigger than 1, so we know it's vertically stretched by a factor of 3. And we also know the sign before 3 is a positive sign. If it's a positive sign, we know it's going to be open upward. Something like this, open upward. So I didn't draw that good. It should touch right here, the vertex. And then we know it's gonna be a minimum because k equals -2, so it is the minimum value right there. Okay, so when we talk about minimum value, we are referring to the y coordinate of the vertex. And the domain and the range, remember these go forever, go up forever. So the domain is the whole real number of x, because every single x on the line you have a corresponding y. Okay, I didn't draw that good, but it's supposed to go up forever. So every single x, I don't care whether it is a negative number for x or positive number for x, we always have a y value to go with it. This is the domain. That's why we said domain are the all real numbers. And for the range, it's a little bit different because there's no corresponding x. When you say have -3, you don't touch the graph, you don't touch the parabola, and any number less than -2 has no corresponding x. So that's why the range only are any numbers bigger than -2 right here. In this slide, I'm going to show you how to sketch the graph of a quadratic function based on the vertex form. Okay, again, we line them up with the generic form of a vertex form. So x minus h squared plus k. And fx or y did the same thing. Right. So first, you know right away, a is 2. And the sign before a is a negative. And h is 1, k is 3. So from this, you know right away the vertex is h and k. So the vertex is gonna be 1 and 3. And we also know the axis of symmetry is x equal to 1. So the vertex right here, 1 and 3. That's what we found here. 1 and 3 right here. This is 1. This is 3. And the next thing, the axis of symmetry, the red dotted line here, is x equal to 1. And the next things is the factor a, which is equal to 2. That means it's going to be vertically stretched because it's bigger than 1. Vertically stretched by a factor of 2. And the last thing is the sign before the variable a is negative, so it's reflection across the x-axis. That's why it's open downwards. And when you say open downward, you have a maximum value at 3. And the domain, if they ask you the domain is gonna be the x value. So x value can be anything because all the x are accountable for. Every single x have a corresponding y. So x are all real numbers. Y is a little bit the range. We're talking about the y. It's a little bit different. Y has to be less than 3. So less than or equal to 3. Because 3 is counted too. So any number less than 3, you have a corresponding x. But if you have any value bigger than 3, say 4 right here, you don't have anything touching the parabola. That's why it's out of the range. That's why the answer for the range is y is less than or equal to 3. To summarize all this transformation from the vertex form, you can say the graph translate up by 3 units and then shift to the right by 1 unit, and we just take a look of the vector A is vertically stretched by a vector of 2. The last one, and look at the negative sign right here, we say it's a reflection across the x-axis. So these are the interpretation or the description of the transformation.